Okay, so now let's get going on our next thought. We know about the relationship between electric force and electric field. We know between force and electric potential energy. We know between electric potential energy and electric potential. Now, what about electric potential and work done, or electric field and potential? So let's start thinking about some of those things. So the first thing we're going to remember is that in a conservative system, the change in electric potential energy, delta U, is the negative of the work done by the internal forces. We also know that work is the integral of F dot ds. So let's fill that part in. So that's negative of the integral of F. Oops, I said F, but I wrote E, F dot ds. So now in this equation, F is the force on the charged particle. F equals Q times E. Those are vectors. S will be the path of motion. So S is the path taken. So a charged particle Q moves along path S. And ds is a small element of the path. So that's our F, that's our ds. What about our delta U? Well, when we were defining our electric potential V, we realized that delta U, our change in electric potential energy, is Q times delta V, our change in potential. Let's put these things together and see what we get. So Q times delta V equals negative the integral of Q times E dot ds. This is important too. This dot is important. This shows us that we're taking the scalar product between the force and the path. Scalar product or dot product. Same one we saw when we were discussing electric flux. In this equation, we've got a Q on both sides of the equation, so we could divide through by Q. And this leads us to our relationship between electric potential and our electric field. Delta V is negative the integral of the electric field over the path taken. This is a pretty important result. Let's put this one in a box. Okay, so this will be added to your list of important equations. This is kind of a big equation. This one is really important. So let's start to think about some of the things that this equation tells us, and what do we have to know here. So first, let's ask what happens if our electric field is constant. So if E is constant. If our electric field is constant, then our integral simplifies to E dot delta S. So then delta V, our change in potential, would be negative E dot delta S. So delta S would then be the displacement of the particle. And there would be two ways to calculate our scalar product. We could use magnitudes and angles. So delta V would be minus the magnitude of the electric field times the magnitude of the path times the cosine of the angle between the field and the path. Or we could calculate it, delta V is negative Ex delta x, this is the component method, plus Ey delta y, plus Ez delta z. Okay, one of two ways depending on what you know about your vectors. So that's one important thing. What do we do if electric field is constant? Let's see, what next important thing can we talk about? What happens if the electric field is perpendicular to the path? That's important. If electric field is perpendicular to the path taken by the charged particle, well, then our delta V would be minus the magnitude of E times the magnitude of delta S times the angle between them. Two things that are perpendicular have an angle of 90 degrees. Cosine of 90 is 0, so this would give that delta V, change in electric potential, equals 0. And this is along, as a charged particle moves along any path perpendicular to the field. Okay, so if delta V is 0, that means V is constant. So we can add another little clause. V is constant along any path perpendicular to the electric field. So this goes back to our equipotential lines. This is why the equipotential lines are perpendicular to the electric field lines, because V is constant along that path there. Okay, so that's what if E is perpendicular to delta S. We might also ask, what if E is parallel to delta S? If E parallel to delta S. What if the electric field lines are parallel to the path taken? Then delta V is minus the magnitude of the field times the magnitude of the displacement times cosine of 0. Cosine of 0 is 1, so I've got the magnitude of the field times the magnitude of the displacement times 1. This is not 0. So this tells us that V will change along any path parallel to the field. Okay, so if we move perpendicular, no change in potential. If we move parallel, there is a change in potential. What else can we talk about? Let's talk about the meaning of this negative sign. That's also important. So let's see. So point number 4. Let's draw a picture of our electric field lines. So here's our electric field E. Let's take our path to be parallel to the electric fields. Let's come along this way. So here's our path, delta S. If we want to find our change in potential, delta V, that's going to be minus, so let's take a constant electric field. That's going to be minus the magnitude of the electric field times the magnitude of the displacement times the cosine between those two things, that's just 0, equals minus the magnitude of the field times the magnitude of the displacement. So we get here delta V equals VB minus VA. So VB would be our final potential, so this would be point B, potential VB. VA would be at our initial point with our initial potential. Delta V, VB minus VA is negative a magnitude times a magnitude that's less than 0. Delta V less than 0 along the electric field line. So this shows us that electric field has to point towards lower potential. VB is smaller than VA. So VB is small, VA is big, small or low, big or high. Okay, so this shows us that electric field lines point towards lower electric potential. What next? So if we know that our potential is negative the integral of E dot ds, we might ask, if we knew our potential, how could we calculate our electric field? So that'll be our last bit. So how can we get an electric field result, a vector, if we start with a scalar delta V? So 5, find E from V. So we know that delta V is negative the integral of E dot ds. So if potential is the integral of electric field, what that means is that electric field is the derivative of potential. How we write that down is we'll say ES equals minus, so that minus comes over here, the derivative of V with respect to S. So S means the S component. Okay, S is the S direction. So let's put this in terms of coordinates that we typically use. And like we did in our wave chapter, this curly d here is pronounced di. That's partial derivative. There. Okay, so in terms of coordinate systems that we typically use, if we use a Cartesian coordinate system, so x, y, z, the x component of electric field is negative the derivative of the potential with respect to x, so how potential changes in the x direction. The y component is negative the derivative of the potential with respect to y. The z component is negative the derivative of the potential with respect to z. So the way they change in their respective directions gives us the component of the field. And to write our electric field, the total vector, we would write it as a vector, the x component in the x direction, plus the y component in the y direction, plus the z component in the z direction. And then the other coordinate system we would use would be radial. So the radial component of the electric field would be the change in potential with respect to the radial direction. So that's if we have to do calculus, if we have to use our derivatives. Sometimes we'll have discrete points. So if we had discrete points, so if we knew the potential at one point and the potential at another point, how would we find the E? There we would say that our x component of electric field would be minus delta V over delta x. So for example up here, delta x would be how far apart these 2 points are, and delta V would be VB minus VA. EY would be minus delta V over delta y, and EZ would be minus delta V over delta z. And we would still write our vector in this fashion. Okay, so that gives us our relationship between electric field and electric potential. At this point, let's just remind ourselves again of our equations and our relationships between our equations. So force between 2 point charges, kq1, q2 over r squared. Electric field due to a point charge, kq over r squared. Force and field are vectors. If we have point charges, the electric potential energy between 2 charges is kq1, q2 over r. The electric potential around a single point charge is kq over r. And then we can fill in the relationships between all of these vectors. So let's see. To go between electric force and electric field, we know that F equals QE and E equals F over Q. So there's a relationship between force and field. Those are between our vector relationships. Between our scalar relationships, we know that U is Q times V, and V is U over Q. So that's the relationship between our two scalars. To go back and forth between scalars and potential, scalars and vectors, we know that the component of our force is minus the derivative of our potential energy with respect to distance. And to get our change in potential energy, delta U, that would be minus the integral of F over the path taken by the charged particle. So there's our relationship between electric force and electric potential. Our last one is the one we just came up with, the relationship between electric field and electric potential. I think I'm just going to twist my paper So I know that delta V equals minus the integral of E dot ds. That's if our E is not constant. If E is constant, then delta V is minus E times delta S, so scalar product both. And to get electric field from our potential, ES is minus delta V over, di V, got to do our derivative for the top one, di S, or ES, if we had discrete points, minus delta V over delta S. Okay, all of these relationships are things we've covered before, but now they're nice and neat and all together in one particular slide, so they'll be easier to find when you're doing some review.